Hi, this is an example problem about standing waves on a string from chapter 17. Pause for a moment and read the question. We can look at this PDF file here that has a compilation of equations that are useful, which are used for standing waves on a string. So you can see the wave speed is given by the tension of the string divided by the mass per unit length, or the linear mass density. And we've also got some relations here for the length of the string in terms of the wavelength and the frequency of the string. And we see that it produces a harmonic series of frequencies, which are given by this integer value n. We're going to explore that in this problem. When n equals 1, we call it the fundamental frequency or first harmonic, and n greater than 1 are called nth harmonics or overtones. So to figure out the frequencies of these guys, we're going to figure these out. So let me go ahead and just do here n equals 1. This is what we call the fundamental. And also below it, I'll do n equals 2, the second harmonic, and below that, n equals 3, third harmonic. First thing we're going to do here is figure out the speed of the wave using the equation. Speed of the wave is equal to the square root of the tension in the string divided by the linear mass density, which is the mass per unit length. We're given these quantities, so it's going to be square root of 80 newtons is the tension, divided by 2 times 10 to the third kilograms for a 1 meter long string. So that's going to be 2 times 10 to the minus third kilograms divided by 1 meter. And when we put those numbers into the calculator, we get a 200 meters per second. All right, so to get the various frequencies, we can go ahead and use the equation for frequency for standing waves on a string. And here it is, Fn equals nv over 2L. And so for the fundamental F1, we're going to just plug in n equals 1. We'll plug in the speed, and we'll divide by 2 times 1 meter. And we'll get our answer here. We can do that in our head. That's going to be 100 hertz, 101 per second, right? Now for F2, notice that this number here, which we just calculated, that's F1, that's the fundamental. So we can always write the higher harmonics. They're just an integer value of the fundamental. So to do the second one, if I want to save myself a little time for F2, instead of going to the whole equation again, I can just write 2 times the fundamental. 100 hertz gives us 200 hertz. And finally for F3, again, an integer value of the fundamental frequency gives us 300 hertz. Now for part B, we want to draw a quantitative diagram of the wave displacement versus position for each of these harmonics. Now I've gone ahead and drawn the baseline, the equilibrium position of the string, and I'm going to go ahead and draw the wave displacement over there. Now for the first harmonic, that means you have the longest wavelength, and you're going to have 1/2 wavelength fit. And this thing is oscillating up and down, so sometimes we draw it like this. In the middle, we have maximum displacement. We call this an antinode here. And we have nodes at the ends. The antinodes are the important ones because you see an antinode corresponds to a 1/2 wavelength. For the second one, we're going to fit a second 1/2 wavelength on, so I need to split it here. It's going to look like this. And if we draw both of them, it's going to look like this. So here we've got 2 antinodes, regions of max displacement. And we've got 1 full wavelength, 2 1/2 wavelengths. For the third one, n equals 3. You see the pattern. That means that we're going to have 3 antinodes, 3 1/2 wavelengths. So let me divide this up into thirds. And it's going to look like this. Oops, we're doing these ones in green. like that. If we draw the other bottom part of it, you know, this thing again is oscillating up and down. We've got 3 antinodes here. All right. Now we're asked, what are the wavelengths for each of these 3 harmonic frequencies? Well, I know that the first one, for example, right, if I think of this as a whole wavelength, right, if I were to continue this here, right, it would be equal to 2 meters, because we know the string is equal to 1 meter, right? And the next one, at n equals 2, we can see 1 full wavelength fits on the string. It's equal to 1 meter. But we can calculate that as well. Let's go back and use our fundamental equation here. Remember that and another equation for the speed here, we can also use this equation that always works. The speed is equal to lambda times the frequency. And therefore, the wavelength, if we solve for lambda, that's going to be equal to v divided by the frequency. So for the first one, we're going to go ahead and get a value of v here. The v is the same for all of them, of course, 200 meters per second divided by 100 hertz or per second. That's going to give us a wavelength equal to 2 meters, as we just said. For the next one, we can go ahead and use the same equation again. It's going to be 200 meters per second, this time divided by 200 hertz, or 1/2. And that's, of course, going to give us a 1 meter wavelength. Of course, you can see one wavelength is going to go the distance of the string, which is 1 meter. And finally, for the last one, same equation again. 200 meters per second divided by the frequency, in this case 300 hertz, or 300 oscillations per second. That's going to give us 2/3 of a meter, or 0.67 meters. And you can see if you break this thing up into thirds, right? 1/3, 2/3, there's your wavelength. Since the whole thing's a meter, that's going to be 2/3 of a meter there. And so that would be our part B here, in a sense. This was our part A. And finally, in part C, we are asked, find the wavelengths of the sound waves created by the vibrating wire for all 3 harmonic frequencies of oscillation. Assume the speed of sound is 343 meters per second. So let me just create a little space here for doing part C. Now for part C, right, this oscillating string is going to move the air at the same frequency that the string oscillates. So the frequency is the same, and we can again use the general equation for wave speed, wavelength, and frequency. Now these are waves in air with the same frequency, so we can go ahead and figure out what those wavelengths are going to be. Again, the wavelength formula, it's going to be lambda is v/f. Frequency is the same, as I said, but now the wave speed is different. Speed of sound, 343 meters per second about at room temperature. And so for the first one, it's going to be a frequency of 100 hertz. The second one, it's going to be the same equation, but now it's a frequency of 200 hertz. And the third one, again, same thing, but frequency of 300 hertz. And in fact, these ones are pretty easy to calculate, since we're going to cancel the 1/2. We will be left with meters, as we want for wavelengths, and then we're dividing by 100, which makes this pretty easy to do. Well, actually, I need to go ahead and use my calculator for this one. That one comes out to 1.72 meters, and the one below that comes out to 1.14 meters. So those are the wavelengths in sound for a wave with the same frequency as the waves on the string.